Hey, okay, so we're going to look at exponential functions today and their transformations. I want to keep this video short, so I'm going to go fast. So pause when you need to and just re-listen. So we know that an exponential function has a formula, like a foundation of this, and y equals c to the x. And that c is our constant or our base, and it's part of the parent. All right, so I guess there's lots of different parent functions, if you will. So for example, like we could have y equals 2 to the x, or y equals 4 to the x, or y equals 10 to the x. And these all have lots of common characteristics, but they're going to change a little bit. So if I was going to make a table of values on this thing, I would start at like -1, 0, 1, and 2. And 2 to the -1 is going to be half, right? Because you need to move it to the denominator. 2 to the 0 is 1, 2 to the 1 is 2, and 2 to the 2 is 4. And then on y equals 4 to the x, if I made a table of values on that, I would have, I'd use the same numbers, -1, 0, 1, and 2. And 4 to the -1 is a fourth. 4 to the 0 is 1, 4 to the 1 is 4, 4 to the 2 is 16, right? And then here, on my x and my y, same numbers, I'm going to keep using the same x's. 10 to the -1 is a tenth, 10 to the 0 is 1, 10 to the 1 is 10, and 10 squared is 100. So you can see that as you get to 2, we go from 4 to 16 to 100. Like these grow exponentially. And you can see that on all of them, their y-intercept, regardless, is 1. So that never changes because anything to the 0 is 1. These all also have one other thing in common. They all have a horizontal asymptote at 0. Right? They're all at 0. Oops, I just missed. So if you were going to go graph these things, and you graphed all 3 of these and kind of looked at them, they would all kind of float along here. They would all cross at 1 and then increase. But what would happen is that they increase at a higher rate because they're all crossing at 1. But they're going to turn and go up. That's a terrible example. They're going to turn and go up that much faster because, oh dear, because at the 1, this thing is up to 2. But at 1 here, this is already up to 4. And over here at 1, this one's up to 100. So you can see that where they really start to like show their personalities, if you will, really happens once they get to 1 and 2, because that's when you see that major exponential growth. Okay, so that being said, we can do transformations to any of these, and their kind of parent function points that we're going to transform should always be the 0 and the 1, because that's really easy. We can also always look at our horizontal asymptote, and then we can, typically look at one more point to help us find transformations. So this time, transformations on exponentials look very similar to what they did on all the other functions we've looked at, especially the vertical. So we've got -a times c to the -b times x minus h plus, oops, I just totally meant to make that blue. Sorry. Plus k. All right, so this is your vertical reflection. This is your vertical stretch. And here's your vertical translation. Here's your horizontal reflection, your horizontal stretch, and your horizontal transformation. So the inside, the things that are happening on x now happen in the exponent. Mapping notation doesn't change. You still have negative x divided by b plus h and negative a y plus k for your mapping. So that hasn't changed at all. All rules apply. You still have to factor in your horizontal, do all that other stuff. Okay, so let's see what this means in some examples. Let's talk about translations first. So if we've got translations, if we've got a horizontal translation, it's going to look like this. Y equals 2 to the x plus 4. So just so we're clear, this 2 is not a transformation. It's part of, it's like your parent function. So the parent function here, the parent is y equals 2 to the x. So you kind of almost have to work backwards. You have to look at what you're given and then decide what is the parent. So it's 2 to the x. So this means we have a horizontal translation, and then our mapping notation is going to be x minus 4y, right? So if I'm going to do this, I'm going to set this up. I'm going to rewrite this and set it up a little different. So if we say y equals 2 to the x plus 4, the first thing you're going to need to do is work backwards and decide your parent function. So we just said that that's y to the 2x. So I would go ahead and make yourself a little table of values that's only for your parent function. Give yourself a -1, a 0, and a 1. And ask yourself where the horizontal asymptote is. We know in this case it's at 0. So 2 to the -1 is half, 2 to the 0 is 1, and 2 to the 1 is 2. So now make yourself a new table of values, but put your mapping notation in it. So our x, all of our x's need to go down by 4, and our y's are going to stay the same, right? So I'm going to take all of my x's over here, all the parent x's, and I'm going to take 4 off of them. So -1 minus 4 is -5, 0 minus 4 is -4, and 1 minus 4 is -3. My y's are going to stay the same. And now I've got my new coordinates. Horizontal asymptotes only change with a vertical translation. So this hasn't done anything. It's going to stay just like this. So now you can draw in your horizontal asymptote. Don't lose that thing because it's really helpful. Go over to -5 and up to half, right? So you're just barely going over. Go over to -4 and up to 1. Go over to -3 and up to 2. And you can start to see your function, okay? When you've got a horizontal or vertical translation, oh geez, all right, so let's say we have y equals, let's go 3 to the x plus 5. So work backwards. What's the parent function here? It's going to be y equals 3 to the x. Remember that base is not part of the transformation. So ask yourself, what would your parent table of values be? Use -1, a 0, a 1, and ask about your horizontal asymptote, which in the parent is always 0. Okay, so 3 to the -1 is 1/3, and 3 to the 0 is 1, and 3 to the 1 is 3. So if we're going to transform that, our x's stay the same because we have a vertical translation, so our y's are going to go up by 5. So I'm going to copy down my x's because they're not changing, and then I'm going to add 5 to my y's. So 5 1/3. 1 plus 5 is 6, 3 plus 5 is 8. Now, red flag, horizontal translations impact your horizontal asymptote. So your new horizontal asymptote is going to be at 5. All right, so I'm going to move my horizontal asymptote up to 5. 1, 2, 3, 4, 5. It's right here. And I'm going to go graph -1 and 5 1/3. So like here. and 0 and 6 and 1 and 8. So it's going to go like this. All right, we just raised the whole thing up. It's pretty straightforward. What's the other? What are those things called? Reflections. Okay, so reflections, same situation. Let's say your original function is negative 2 to the x. A lot of times we'll put brackets around that to help make it really clear. Well, what is the parent function here? Go back in time. The parent function is 2 to the x. Again, quick table of values. Negative 1, 0, 1, horizontal asymptote. Negative 2 to the negative 1 is a half. 2 to the 0 is 1. 2 to the 1 is 2. Transform. I feel like I'm a transformer, like a little kid. Okay, this is a vertical reflection, so your y's are going to be negative, your x's are going to stay the same. Negative 1, 0, 1, negative half, negative 1, negative 2. Boom. Your horizontal asymptote, don't forget that thing, hasn't changed. It only changes with a vertical translation. So your horizontal asymptote is still right on the 0. And you're going to come over here and you're going to this time go negative 1 half. Wow, that's terrible graphing. 0, negative 1, 1, negative 2. So it's going to do this. Okay? The same thing is going to happen. That's a vertical reflection. I feel like you can figure out the vertical or the horizontal reflection. It's going to do the same thing just to the x's and not the y's. A stretch. Okay, stretch. Let's talk about stretch. So let's say a stretch looks like this. What if we have y equals 2 to the 3x? Okay, so back this train up. Your parent function here is 3 to the x. Okay, the 2 is an a value. So your parent function on this, your table of values is negative 1, 0, 1, horizontal asymptote. 3 to the negative 1 is a third. 3 to 0 is 1. 3 to the 1 is 3. So we're going to stretch our y's. So we're going to double our y's. Our x's aren't changing. Is my horizontal asymptote changing? No. What is 1/3 times 2? 2/3. What is 1 times 2? 2. 3 times 2, 6. Okay. So my horizontal asymptote didn't go anywhere. Go highlight that thing so I don't miss it. Now I'm going to say negative 1. I should put some lines on this graph. Okay, negative 1 is going to 2/3. And 0 is going to 2. And 1 is going to 6. So you can see this thing is stretched. But the direction didn't change. It didn't shift up or down. It's just going to get bigger faster. All right. That's kind of it. I mean, it's all stuff you've seen before. So last one, we'll do like a little combo here. What if we have 2 to the negative x plus 4? We've got two transformations happening here, but first ask yourself, what's the parent? And the parent is y equals 2 to the x, all right? And for the 90th time, make that your table of values, and you're going to get half, 1, and 2. Transform those, horizontal asymptote at 0. Transform those. You have a negative x, and you have a y plus 4. So negative 1 is 1. Negative 0 is 0. Negative 1 is 1. Half plus 4 is 4.5. 1 plus 4 is 5. 2 plus 4 is 6. Horizontal asymptote is 0 plus 4 is 4. Graph. 1, 2, 3, 4, 5, 6. My graphing skills just get better and better. 1, 2, 3, 4, 5, 6. Put your horizontal asymptote out. It's at 4. Okay, and we're going to go over to 1 and up to 4.5. And we're going to go over to 0 and up to 5. And we're going to go over to, oh, that should be -1. -1 up to 6. And it's going to do this. Okay? That's it. You're done. You're a genius. Congratulations.